We'll take a look at finite. We'll take a look at infinite series. Talk about what they are, a little mathematical definition, and then try a couple of examples here. So I had someone ask in first period, why do we need to use these? And just one quick application out there in the real world is that when we get into some of the series that we're going to talk about later in the unit, you'll see they can be used to approximate like how much money you have in your bank. It can also be used to calculate how much medicine is still left in someone's body. It's sort of, in some ways, it can be related back to like the half-life of something in science. That's really a series. You're looking at your half-life, like how much remains, but if you add that all up, you can get a series. So we have two types of series here. We'll talk about the one that I think probably will make more sense for you, and that is your finite series. So a finite series is just the sum of n terms of a sequence. And I should say the first n terms we'll put the first in here, n terms of a sequence. And I say that because typically you're going to start with the first term and go up to a certain term. Now, occasionally we'll do something called a partial sum where we'll go just a piece of that sum. But that's the basic definition. So it's also sometimes called the nth partial sum. And we will actually look at that today to help us with an infinite sequence. I want to look at how this is written mathematically, and there's a special symbol that we're going to use here called sigma, and that sigma is the Greek letter that looks almost like an E. That is a sigma. So if you've ever heard of fraternities and sororities that use sigma, this is what that looks like. That is a capital letter. The capital sigma. All right, so we're going to have some pieces in here, and I'm going to write them all in, and then we'll talk about what they all mean. Underneath the little sigma, we're going to see something like, it doesn't always have to be, but like I equals 1. On the top part of that sigma, we're going to have some number. We're going to say n for now. And then here will be like our a sub I notation. So what do all those variables mean? That's going to be the important part here. So first of all, this number that's underneath, so this part here, is the first number in your sequence. So the first number you're going to add to your sum. Okay? We're going to start with I equals 1. This is the last number we'll use from our sum, or use from our sequence. So it's giving us a range of numbers that we're going to use. Okay, so maybe the bottom number is 2 and the top number is 5. That means that you're going to use terms 2, 3, 4, and 5 and add them together. And then this guy is think of it as your generator. Okay, so it's the generator for our sequence. We'll say sequence generator. In other words, it tells you how to calculate each term. Okay, it's going to be your formula, so to speak. Sometimes you'll see the letter K instead of I. Don't be alarmed by that. It's just those, and maybe even sometimes J. I, J, and K tend to be used a lot when we're talking about this idea of a series. So don't get confused by a different letter. But what this is going to be equal to So let me maybe zoom back out here. So this, we would write, I'll just write equal to out here. Probably could have written that sequence generator somewhere else, but that's okay. It'll look like this. We're going to take I sub 1 and add it to I sub 2, I sub 3, all the way up to I sub n. Or I'm saying A sub n. So we're going to take all of the terms between the first number we see, so in this case 1, up to and including the nth term, and we add them together. So instead of just listing the terms like we did in a sequence, a series is the thing that adds those terms together. Okay, so that's our finite series. Let's do an example of a finite series right now, and then we'll go and talk about the second term, or the second type of series. So with a finite series, let's do a couple just quick examples here just to get the feel of things. Hi. I lost my example here. All right, let's do a couple quick examples. So example 1, we're just finding the sum of the finite series that we're going to have here below. And these are finite. I wanted to try to keep that on the page, but I don't think I can. All right, so here we go. We got our sigma. I'm going to have us start with I equals 1 and go up to the 5th term. So that means go from the first term to the 5th term using this as our generator. So 3 times I is our generator. So whatever I is, we're going to multiply it by 3. Give us the terms of our sequence, and then we add them together. So what that looks like as we go through this process is this. Think about what happens when you have I equal to 1. When I is equal to 1, we plug in 1. 3 times 1 gives us 3. Okay, so then we're going to have I equals 2. What happens when I equals 2? What do you get? 6, right? So 3 times 2 is 6. We're going to add that to 3. What do we get when I equals 3? So 3 times 3, we plug in basically 3 into this guy here. And 3 times 3 is 9. So we're going to add that to our previous numbers. And we're just going to keep going until we get to I equals 5. So now we've got I equals 4. What do you get when I equals 4? 12. Good. And then finally, I equals 5. And this is where we'll stop because that's our upper limit. What's 5 times 3? 15. Okay. And then all that's left to do is add these all together. So 3 plus 6, that's 9. Plus 9 is 18. Plus 12 is 30. Plus 15, 45?
Yes.
Okay.
So we stopped at 5 because 5 is on.
Yes, we stopped at 5 because of this right here. That 5 that's at the top. Right, so we go from I equals 1 to I equals 5, and we just generate all of the terms of that sequence, and then we add them together. That's all a series is. So it's very much like a sequence, except now we're just adding the terms together. The notation is what can get a little tricky. We just got to get used to it, that's all. Okay, so that would be our first series. Let's do another one. I'll use green. I should be using green all day.
I know, my whole notes are using green.
I just thought of that. St. Patty's Day, I should be using green. All right, so let's do a series where we go from I equals 3 up to 6. So our first number that we're going to add together is what we get when we plug in I equals 3. So instead of starting with I equals 1, we start with I equals 3. And we're going to find each term of the sequence by plugging it into 1 plus I squared. And I'm going to do this the same way. I'm going to think about what do I get when I is equal to 3? And I'm writing that down, just keeping myself organized so I don't skip over terms. Okay, so what do I get when I equals 3? 10, good. So my first number I'm going to add is 10. How about when I equals 4?
17.
17, good. When I equals 5,
26.
26, good. And when I equals 6,
37.
37. Awesome. Add all those together.
I have a question.
Yeah.
What is like the I equals 3 at the bottom? Oh, is that the, never mind, it's not just start with.
Yeah, that's the number you start with. We have to have a starting place and an ending place, so that just tells us where to start and end. Okay, what is that? So 27 plus 26, that's 53. Plus 37, is that 90? Hope so, because that's what we got first period. But I'm always checking, because sometimes they're a little sleepy first period, and they let me make mistakes. Not always, but every now and then. But I think it's 90. I think we're good. Okay. That's all a series is. That's a finite series. That means that we have a specific start and end. We can calculate those numbers because we have a specific place we're going to end up. The second type of series, so that was the first type. Second type, I'm going to use yellow just for a minute, is an infinite sequence. Series, sorry, not sequence. I'll just say infinite because we said finite up top. So infinite. An infinite series is the sum of all the terms in an infinite sequence. So it's the sum of all the terms of an infinite sequence.
Are these the only 2 series we're going to do?
Yep.
Okay. Thanks.
Yep, just 2 types of series. Now, let your mind kind of think about that for a second. I'm adding you to add up an infinite number of things.
So it's infinite.
It seems like that would be a logical conclusion, right? But that's not always the case. Sometimes we can add up an infinite number of things and get a specific sum. Now that seems completely strange and doesn't make a lot of sense. But I think once we go through an example, it'll help a little bit. Let's make sure we can write out what this looks like, just in general terms. So an infinite series starts out looking very much the same way. We still use that sigma notation. We still generally start out with like I equals 1. I don't know that normally you're going to have I equals 0, but I suppose it could happen. I don't know that it will, but this top number is going to be infinity. That means we're looking at every term in this sequence, and we're adding them together. And then we'll still use that same notation, a sub I. But when we write this out, we're going to have a sub 1 plus a sub 2 plus a sub 3. We're going to get to that nth term, and then we're going to keep going. So we can't write what the ending looks like because we can't see the ending. Infinity is an idea that we've used. It's not actually something that has a specific value. So when we talk about infinity, we're saying, imagine if you could go on forever and ever and ever and never stop. What's going to happen? And when we looked at limits at the beginning of the year, we kind of touched on that a little bit as well. So what does an example of this look like? Because it seems really strange that we could find the sum of something that goes on forever. So let's find the sum of this infinite series. And I'm going to put down here using partial sums. We'll talk about what that means in just a minute. But first I have to give us a series that we're going to use. So my series I'm going to use here looks like this. Let's go from I equals 1 to infinity. And we're going to use the series generator as 3 divided by 10 to the I power. And I'll blow that up just a little bit so you can see what that says. So I equals 1 up to infinity. And we find the terms of our series by doing 3 divided by 10 to the first power. Now jumping right in, if I try to figure out what this is as an infinite sum, it might be tricky. So I'm going to pause with the infinite sum and say, okay, let's imagine we just had a partial sum. We had a finite sum. So let's look at, let's say the fifth partial sum. Okay, so let's look at the fifth partial sum. What do I mean by that? Well, I mean take that sequence, or take that series, and instead of going to infinity, go to 5. So what we're doing here is we're imagining that we had this problem in front of us.
Are we just making a finite series at this point then?
Yes. We're going to use a pattern that we see in the finite series to try to make a conclusion about what's happening in the infinite series. That's our goal. Yeah. So we're pausing the infinite series for a minute and just saying, hey, let's just look at a chunk of this and see if we can make sense of what's going on. Yep.
So, how would you determine
How far to go? Yeah. There's no rhyme or reason to that.
Okay.
I just chose 5 because hopefully by the 5th term, I'll be able to see a pattern.
Okay.
Sometimes you can see it earlier, but we're just choosing 5 as a random kind of arbitrary number. Okay, so let's do this. Let's just calculate this partial sum. So we're using this to help us determine what's happening in the infinite sum. And that seems weird, but once we get going, you'll hopefully start to see why we're doing this. So what happens when we get I equals 1? Now here's the thing. I've told you all year, give me your answers as fractions. Haven't I? I'm going to change my tune here for a minute. Tell me what this is as a decimal. So 3 divided by 10 to the first power. So that's just 3 divided by 10. What is that?
0.3.
Yep, 0.3. Okay, to that, we're going to add the second term. So now we have 3 divided by 10 squared.
0.03.
Good. That's 3/100ths, which is 0.03. To that, we're going to add the third term.
0.003.
Yes. Are we starting to sense what's happening here a little bit? Hopefully. What happens when we get the fourth term?
It's going to be 1 decimal plus 0.
Yeah, we're just adding on another 0 in front of our 3. Okay, what about the fifth term? Same thing, right? So add on one more 0. So instead of having 1, 2, 3 zeros, we're going to have 4 zeros. All right, now, that's our fifth partial sum. Let's actually calculate what that is. And you could do this with a calculator. I don't think we need to. But, if you wanted to line this up like you did in elementary school and add these numbers together, we would have something that looks like this. 0.3 plus 0.03 plus 0.003 plus 0.0003 plus 0.00003. Right? What does that add up to be?
0.33333.
What do you imagine is going to happen if I find the next term? I'm going to add another 3 on, right? So let's take this, what we're doing, and come back up, and I can put this all back up on the board here in just a minute, guys, if you need it. What we have so far is this, right? Now, if I keep adding on 3s, if I go to the 6th term, then the 7th term, then the 8th term, then the 9th term, we just keep adding a 3 on to the end of that. That 3 at the end is just repeating, isn't it? We keep adding on 3s and adding on 3s and adding on 3s. What would happen if we went out for infinity? What does this start to look like it's going to be?
1/3.
1/3. That is the sum of that infinite series. That series that has an infinite number of terms will all add up to 1/3. Okay? So something that has an infinite number of terms can add up to a specific number. All right. So the idea here is to break that infinite series down into maybe a partial series and look for a pattern. If you find a pattern, sometimes that'll lead you to what that infinite series is going to be. Sometimes there isn't a pattern. Sometimes we try and we see these series just not converging upon a single value. We're going to talk more details about that at a later time. But for now, I want you to just kind of have an introduction to what a series is. Now, imagine I gave you something that looks like this. So now I want you to, we'll do one more thing and then we'll finish up today. Write the sigma notation for the series given. Now, what on earth does sigma notation mean? That's just that E thing. Okay, so when I say sigma notation, that's that notation that uses the E. So let's say I give you this series now. I'm going to write out what the series terms look like. I can't just give you a sum and expect you to come up with the series right now. That doesn't make sense. But I could give you the terms of that series. So maybe it looks something like 7 times 1 plus 3. Nope, we'll just do 7 times 1. Plus 7 times 2, plus 7 times 3, plus, and let's go all the way up to 7 times 25. Okay, so I'm not asking you to come up with the actual sum. Keep that in mind, right? I'm just asking you to write what that sigma notation would be for that series. How would we represent that in sigma notation? So we want to come up with what it would look like in this form. That means we've got to come up with the lowest number that we're plugging in for I. We've got to come up with the highest number we're plugging in for I. And then we've got to come up with the generator. So I tend to look at, is there an I that I can isolate in that sequence or that series the way that it's written? In other words, I look for that thing that's increasing by 1. In this case, I see this. We start with I being 1, and we go all the way up to I being 25. So I know that I begins with 1 and ends with 25. And then all I have to ask myself is, what am I doing to I to find each term? So what is my sequence generator, in other words? What do you think? 7i. Okay.
Can we do the n for 25?
We write what you don't have to write n equals, you can just write the number.
Okay.
Yeah, so that's a great question. The notation is we just write the number, not that it's n equals that number. Because nowhere in my sigma notation do I have, like it's 7 times I. If I throw n in there, I've got to then account for what n is. N is just your ending number. Think of it that way. I could give you, something like what we've done in previous ones, in previous lessons. Maybe I give you something that looks like, I don't know. Let's do one more here, just to have fun with this. Let's say I do 1. Got to get my green pen again. 1 times 1 plus 1 times 2 plus 1 times 6 plus 1 times 24 plus yeah, that works. We'll just leave it at, I'm making this one up as I go. Let me change one thing in this. I'm going to change these first numbers. So we'll make these 1, 2, 3, 4. I think that'll work. Okay, we'll go all the way up to, let's just stop there because I don't want to calculate the ones beyond that. So we'll just stop with that, 4 times 24. Okay, how can we write the sigma notation for that? So we need three things. We need to know what I starts with.
I equals 1.
So it starts with I equals 1, right? We see that thing counting up. This would be my I. It goes up to what?
24.
Careful.
4.
4. Whenever we look at I, we're looking for counting by ones. So we have our first term, our second term, our third term, our fourth term. Good. And then how am I going to write the sequence generator for this guy? So it's something times I. So I times what? What do you notice about that
Oh,
sequence?
it's a factorial.
It's a factorial. So it's just I times n I would say I times I factorial, I guess, is how I would have to write that.
How would it be 5 times 5 factorial? This is only 4 times 3 times 3 times 1.
So it's
Can it just be I factorial because it doesn't take like.
if it were just I factorial, I wouldn't have these numbers here. The 4, the 3, the 2, and the 1. That's my I. And then what I'm doing to get each of those other numbers is I'm doing I factorial. Like this number here is I factorial, right? So we're multiplying I times I factorial in this case. Now I could have just given you 1, 2, 6, 24, in which case our sequence would just be I factorial. And we would still go from 1 to 4. But it's possible that you could be given things that we've done before and have to come up with the sequence generator just like we've been doing. You'll just write it in terms of I instead of N. That's the only difference. And then figure out what's your first term, what's your last term. Any questions? Like I said, this is an introduction to Unit 9. So we're getting our feel for what a sequence is, what a series is, and then we're going to start to sort of hone in on the more particulars. So later this week and the next week, we're going to talk about arithmetic sequences and series. So we're going to be really focused on that type, even though we've already seen arithmetic sequences and series. Okay, but we're going to just kind of focus in on that. And the next time when we come back from break, we'll talk about geometric sequences and series, and then some induction and all that kind of stuff.